Okay, I think we can get started. Today we will introduce CLIP, Contrastive Language Image Pretraining approach. So it's an approach for combining language and vision for training image classification systems. The first innovation of this paper is that it uses pre-training task of prediction language supervision associated with image to train image classifier and to learn image representation. This training task, this pre-training task, is more like a retrieval task. For example, for a given image, you want to find the corresponding language text sequence associated with it. Similarly, for a language text sequence, you want to find the corresponding images associated with it. And then this paper shows that this approach is very effective and also scalable. The second innovation is that it uses natural language as a reference of learned visual concept. And this can enable zero-shot transfer learning to unseen tasks. Besides, it can expand the visual concepts learned beyond a single data set. For example, for a given data set, it can only have a given number of class names. But when you learn the model to predict the text associated with each image, then those text is more descriptive and more informative, and there are more concept in this language. And then the limitation of this paper is that it only did the evaluation for classification tasks in different setups. For example, and zero-shot learning and few-shot learning, linear probing and fine-tuning. I think the intuition of this paper is also quite simple. The key idea is to align the visual concept and language concept to achieve better representation learning capability. And since language concept is more informative and the text representation is more flexible and extendable, that means we can learn a model that can have better understanding, can learn better semantic meanings. And some future directions on top of this work include interpretable AI. For example, in medical image analysis, usually after we get the prediction result, we want to see why. And for example, in cancer detection, this cancer can have different attributes, and we want to predict all these different attributes. And this attributes information can be easily incorporated in the language text, and then which can be used. This can be used to train the model. Another direction is we can train models which can generalize to non-classification tasks, for example, segmentation and detection. And this paper is published in 2021 at the ICML, International Conference on Machine Learning. So first, the motivations of this paper. The first motivation of this paper is that we have seen like a success of task-agnostic objectives in language models. For example, this auto-regressive and mask language modeling. And development of this text-to-text as a standard input-output interface enables the task-agnostic architecture to zero-shot transfer learning for downstream tasks. And second motivation is that so language and some language supervision can provide a flexible and more context-rich annotation. And that means we no longer need annotation to be the classic machine learning compatible form. For example, in image classification, the label is always encoded as a one-hot representation learning one hot representation, and quite some techniques are proposed to better design the label representation. For example, the soft label label smoothing. And some motivation of this paper is that we want to align the visual concept and language concept. That means for given language concept, we want to see what does it mean when we have an image. So basically, we want the image to demonstrate the concept of particular text in the text format, and it can enable the flexible zero-shot transfer learning, and such data set, basically image text pair data set, is available in large scale. Now, the big picture of this paper is like this, of the whole approach. During the training process, we have a text encoder and image encoder. The text encoder will give us a representation of the text prompt. We call this text prompt, and the image encoder will give us a representation of the text of the image. So once we get the representations for all the text prompts in a batch, and also the image representations in a batch, we can calculate the contrastive loss by basically calculate dot product, inner product of them, and then follow the regular contrastive learning to do that. And the intuition of this approach, of this training approach, is that for a given image, we want to find the text prompt associated with it for all these images, and for each text representation, we want to find the image representation that is associated with it. So in the training process, we actually want to maximize the algorithm items, because they are the correct correspondence associations. But for the off-diagonal elements, we want to minimize them. So here is the training process. So what about the inference process? The inference we have a sequence of text prompts. They basically encode the class label information, and we will use the text encoder to get the representations for all of them. So for a given image, we will first get the image representation of this image, and then we will calculate the distance between this image and each of the text prompt representation. And this is simply the cosine similarity. Then when we assign the label, we just choose the text prompt which has the smallest distance from the image representation, and the corresponding text prompt will be the label of this image, and we can get the class label information from the text prompt. Then in this situation, we get the prediction for this particular image. Now, the training protocol, as I mentioned, for given batch size of n, we have n pairs of images and text, and it's actually assigning the correct text representation for each image, and also assigning the correct image representation for each text prompt. I think the intuition for this pre-training task is that we use more descriptive text prompt as supervision. I'll demonstrate later why it's more descriptive, and also why it's more informative. And the model training this way is called CLIP, Contrastive Language Image Pre-training. And the procedure code is really simple. So we have image encoder to get the image representation, and text encoder to get the text representation. Then we calculate the cosinity, like the distance, and then we calculate the loss based on the cosinity similarity. and then we minimize the loss to train the model. Now at the inference, as mentioned, so there are several steps. First, the class names. For example, for given data set, there are particular number of classes. So these class names will be used to design the text prompt. And this text prompt will be used by the text encoder to generate the text representations. And the image representation for each given query image will be used to calculate the cosine similarity with each of the text embeddings. Of course, there are some other tricks, for example, temperature and the particular function to calculate the probability. Yeah, these are minor things. And the key thing is we will assign the class name label corresponding to the highest score text prompt to the image as a predicted label. I think one important trick that can happen in this framework, CLIP framework, is the prompt engineering, basically how to design the text prompt based on class name labels, because different text format can lead the text encoder to give different text representations. These representations can greatly affect the final prediction result. Now, let's talk about the text prompt. So in regular image classification, for example, we have a set of images, and we have the corresponding class names, or these labels. And usually we do the one-hot encoding. For example, suppose this first image is in the class 0, and the second image is in the third has a label 2, and the n-1 image has a label c-1. For all those labels, we first do the category representation, and then we convert it into like a one-hot representation. These one-hot representations are what actually used during the training process. For example, once we get the probability prediction from the classification model, we will calculate the cross entropy between the predicted probability distribution and this one-hot label distribution to calculate the loss. Now the thing change here is that instead of using the one-hot representation, also instead of using this category label representation, what we do is we directly encode the class name as text prompt, and this text prompt will be fed to a text encoder, and it will give us a set of text representations. We can treat this representation as the label representation, and they can be used during the training process to train the model. Similarly, during the inference process, we can also use them to determine which class label we should assign to the image. I think that as I mentioned, at the inference time, we just calculate the cosine similarity between each text prompt with the image, and then we just assign the text prompt which achieved highest similarity or lowest distance as the image label. And there are some ways we can do this text example. For example, we can, for a particular image, its corresponding class label, we can design quite some text prompt format for it. And the text encoder can give us the corresponding text representations. We can combine them to get an ensemble text representation. This representation can be then used to calculate cosine similarity and then determine the corresponding label associated with the image. So what the difference between this text prompt supervision and this one-hot representation supervision. I think there are quite some difference. So the first thing is for the one-hot representation label, we can only handle a fixed number of classes. For example, we need to know in prior the number of classes associated with a given dataset, and the softmax classifier is actually static. And for the text supervision, since the text encoder has already learned how to align the text concept to visual concept, that means we can have an arbitrary number of classes. For example, even though some classes are not seen during the not seen in the dataset, we can use the corresponding text prompt as a like a potential label, and we can get its corresponding text embedding, and then we can calculate the distance between it and a given query image. Yeah, we can follow the same procedure to use the cosine similarity to determine whether it should be assigned for given query image as its label. Now, so here are some concrete examples about how we can design the text prompt. The vanilla text prompt format is we directly use the class name label instead of using the one-hot representation label or category label. So this another format is engineering the text prompt. For example, we can use a photo of the class name label. So this will be the text prompt taken by the text encoder to generate the text representation. And there are some other ways to do that. For example, we can add some extra explanation, a photo of a particular class name label and what it is. It's actually a type of food. Similarly for this other type of formats. And then one thing I want to mention particularly here is, yeah, it can really handle the fine-grained visual classification. We can incorporate for example, for this buttercup and the daisy flowers, we can add quite some attribute, for example, its shape and its color and its size, etc. Now here is a demonstration for the classification and the inference. So the candidate class labels are a set of text prompt. We calculate their corresponding text representations and calculate the cosine similarity between them and the corresponding image representation. And then we just assign the highest scoring text prompt to the image as its label. For this text prompt as supervision approach, I think that there are quite some works already existing in the literature. From the earliest work is published in 2013. And after that, we have quite some works appearing in the community. And under this particular framework, I think there are some really critical questions we need to be aware of. First, how to design the label set, and what class categories to use, and how to design the text prompt format, and also what kind of language to use, like English, Chinese, Japanese, etc. And also how to determine the cosine similarity threshold. It's more like a hyperparameter there. Now, so suppose we train a model in the previous way, what kind of capabilities does it have? So here are some of them. But the first thing is that it has really strong zero shot, a single shot, a few shot learning capability. So we will show that later, and it also give us really good representation when you compare it with previous representation learning approaches. Besides, it can improve the robustness and the performance in the domain adaptation scenario. The final capability of it is that it can also improve the fairness and reduce biases. Okay, here are some evaluation setting. So the zero-shot inference means that we do not fine-tune any part of this model or anything else for the downstream task. We directly use the model for evaluation. And the fine-tune setting is a particular situation where we will update the feature backbone and also potential task ahead there. And for the linear probing evaluation, we only update the task head, but for the feature backbone, it's fixed during the downstream task evaluation process and the training fine-tuning process. Now, here is a demonstration about how the prompt engineering and the prompt ensemble can affect the performance. So this blue curve shows us the result using this vanilla prompt, text prompt without any extra context information. And the green one is the performance associated with text prompts that are well designed and engineered. Seems for these two particular scenarios, this prompt engineering and ensemble can really give us significant performance improvement. Now let's now talk about the zero-shot learning capability. Here is the performance benchmark. So this paper evaluates the model over quite large number of data sets. For example, for all those first more than 10 data sets, it achieves really significant performance improvement, especially for the Stanford card data set. It's more than like it's almost like a 30% improvement. And for some other data sets that the proposed approach does not show any improvement, for them, these data sets are more like specialized and complex data set, and they are all about really abstract tasks. For example, this error set and reset 45, they are about SATnet images. So without fine-tuning over those data sets, it's really hard for this model to achieve really high performance. Similarly for these medical images, patch chameleon, the zero-shot evaluation cannot give us any performance gain. Okay, here this number like 7.7 is the performance score gap between the accuracy gap between this clip, the zero-shot clip, and or linear probing fine-tuned ResNet 50 model. So that means the baseline here is a ResNet 50 that is fine-tuned for each particular data set. But for this clip, we do not fine-tune it in any way over any of this data set. I think that, so for this particular project, if we compare this clip with previous zero-shot learning approach, the performance is really significant. It's for example, for this particular situation, it can achieve an improvement of like 65% almost. Now here is another really interesting observation for the zero-shot learning clip. It seems we really did a large model. Okay, here for this resident 50, resident 101, resident 50 times 4, it's like a scaled up model of this resident 50. So with increased size for all these models and increased compute, and performance can go up consistently. It seems in some of the previous works, for example, this Kaplan 2020, the authors shows that the performance of deep learning system is actually predictable as a function of the training compute and also the dataset size. Yeah, that's a really interesting work there. So in this paper, the authors conjecture that when scaling has so far, while the scaling has so far steadily improved performance and suggests a route for continued improvement, the authors estimate that we need around 1,000 times increase in compute so that we can have a zero-shot clip to achieve performance comparable to the state of the art. Now, let's now talk about the few-shot learning setting. So in this particular setting, we will have some examples from the downstream target data set for fine-tune the model. And even for this, even in this situation, there are two ways to do that. One way is we only fine-tune the classification head. Another way is we also fine-tune the feature backbone instead of, or apart from the classification head. So here, so the situation where we update the backbone and the classification head, we call it the fine-tuning, a fully supervised fine-tuning. For the situation where we only update the task head, we call it the linear probe evaluation. So the tuning process is very similar to the regular image classification training with the image label, probably like a one-hot representation, and we get the probability score distribution prediction. Then we calculate cross-entropy loss. This loss is used to update the model. Now about the performance, for them, if we focus on the model trend in this paper, seems at a really few shot learning, for example, 1 shot or 2 shot, for those two scenarios, their performance can be even inferior to the 0-shot learning situation. So I guess it's probably like a this 1-shot, 2-shot learning, it destroyed the alignment of the language concept and visual concept on the one hand. On the other hand, there's two examples, one example or two examples are not enough to learn a really good representation in the supervised learning situation. And this is really different from the human behavior. For example, in the zero-shot learning situation, the human can achieve a pretty low performance, but once we give human one example to demonstrate the learning, the human can improve its performance significantly from like a 53 to 75. But for this clip model, it seems it's quite different. Actual, like a few actual learning examples can even compromise the performance here. Now let's talk about the fully supervised linear probing tuning situation. So in this plot, the authors demonstrated the relation between a linear probe clip performance and the zero-shot clip performance. Basically, for the zero-shot learning, we direct do the evaluation without fine-tuning. But for linear probing, we only update the task head. We plot the corresponding result in these two situations. Then we get this plot. It seems the linear probing can always give us better performance than the zero-shot learning models. I think it is also quite intuitive that the for particular data set, it's better we fine-tune the model on top of it instead of directly using the model for inference on top of it. Now here is a plot for demonstrating the relation between the model performance and the compute. Say according to this plot, it seems more compute there is a positive correlation between the model prediction performance and the compute needed for the model. And it also shows that when you have a higher resolution input image, you can get a higher performance. Now, so we talked about the performance of this clip model in the zero-shot learning situation. Now, what about the fully supervised linear probing tuning situation? It seems when we fine-tune this model by only updating the task head, we can already achieve really significant performance improvement. For example, we have much more data set for which we can achieve performance gains here. And for those data set we do not achieve performance gains, I think that the gap is pretty small. Yeah, it's fairly comparable to the state of the art. Now, we talk about another situation that is used by the authors to evaluate the model. It's about the out-of-distribution robustness. So this situation, it concerns about when we train a particular model on a particular data set, at inference time, we may have a data distribution that is quite different from the data that we use to train the model. And we want to see how the model will perform on the inference data set. Since those two data distributions are quite different, so we call it like a out-of-distribution robustness. Similar for this clip model, it can achieve really good out-of-distribution robust, at least better performance than the standard supervised training. For example, here, these blue dots are the performance associated with models trained in the standard fully supervised learning way. And for this purple curve and this purple dot, they correspond to the performance of a zero-shot clip model. And these gray dots are associated with the models which incorporate the techniques for improving the robustness of models in the supervised learning setup. So the zero-shot learning model can achieve like a performance closer to this dashed black curve here. So this dashed black curve, it indicate the performance where we achieve similar in data distribution, in distribution performance and out of distribution performance. Usually we expect that the out of distribution performance will be worse than will not be as good as the in distribution performance. That means those dots, those curves should be below this dashed black curve. And for curves which are closer to this dashed black curve, that means they have a better out of distribution performance or out of distribution robustness. But here is another angle for inspecting the out of distribution robustness. For example, for all this data set, each row is a data set. For all this data set, there are variants of a particular data set. That means all the classes, they are the same, but those image content formats, they are very different in each data set. So when you check the resident 101, which is trained on ImageNet, it can achieve really good performance on the ImageNet dataset. But when you evaluate on the ImageNet V2 and the ImageNet R, then the performance is really bad. But for this zero-shot clip model, it can achieve really high performance consistently over all this dataset. But also investigated how these different techniques can affect the robustness of the clip model. More specifically, they consider two particular techniques. One is the adaptation to class shift. Another technique is the adaptation to ImageNet. So for the adaptive for the adaptation to class shift technique, in this particular situation, we will adjust the text prompt according to each particular data set. And this technique, it seems, according to the result presented here, it can improve the performance for the particular data set. And this ImageNet zero-shot clip is actually static zero-shot clip without any adaptation. And this logistic regression clip, it's a fine-tuned clip on ImageNet dataset in a fully supervised setup. So from this plot, we can see that the adaptation to ImageNet can improve the prediction accuracy. For example, prediction accuracy of this prediction accuracy on top of this ImageNet, but it can compromise the performance on the other data set. So that compromise is more like a robustness issue. This red curve is moving away from this dashed black curve, not here. Another observation is that the adaptation to dataset specific class set can improve the robustness. That means it can push the corresponding curve closer to the dashed black curve here, not here. Another quite interesting observation is that we observe kind of a linear relation between this in distribution performance and this out of distribution performance. Means for all these data points, we can get a really straight line here. And for the models which are trained in the standard supervised learning way, they have the worst out of distribution robustness. You see, it's the furthest from the dash black line here. Now here is another perspective for checking the out of distribution robustness. It means for apart from zero-shot learning model, these few-shot learning models, and even for the model which is fine-tuned in the fully supervised setting, all of them achieve a much better out of distribution robustness than the other models here. Now, we talk about the bias evaluation of the CLIP model. It means for this CLIP model, if we follow the regular approach like text prompt engineering and all these inference pipelines, we can get quite different prediction performance for different races, colors. For example, here in this particular data set, we want to do the classification of people from different races. Seems for the Black people and the East Asian, this model is more likely to predict those people faces as something bad. But if we do something on top of the label set, for example, we add one extra label, then this performance, this bias can be alleviated. Okay, I think that's all. Thank you.